This is Physics 2212, Lab 4. The purpose of this lab is to predict the behavior of circuits, use multimeters to measure the values of conventional current and potential differences in the circuit, and examine the behavior of ohmic resistors and capacitors. A brief preview, we find that I1 is equal to I2, and that our RC is 5.958 seconds, which is a 0.7% error. Because of energy conservation, we know that delta V capacitor plus delta V resistor is equal to 0. We also know that delta V is equal to Q over C. So we can rewrite our equation as Q over C equals, or minus I over R is equal to 0. And I is equal to negative dQ dt, which is the amount of dQ flowing off the capacitor in a time dt. So we can rewrite our equation again to be Q over RC plus dQ dt equals 0. Because delta V across the capacitor is proportional to Q, this is also the differential equation for delta V. So we can find that delta V is equal to delta V naught e to the negative t over RC. And a plot of natural log of delta V over delta V naught versus t should give us a straight line with a slope of negative 1 over RC, where RC is the time constant of the circuit. Our first experiment, our system includes a circuit and the surroundings is everything else. Our initial conditions is two 1.5 volt batteries, a 47 and 100 ohm resistors, and two ammeters. We assume that the ammeter introduces a 0 ohm resistance, which we will carry this assumption throughout the experiment. So we can find that our I1 is equal to 0.02 amps and I2 is also equal to 0.02 amps. If we flip one of the ammeters around, we get the same value, but it's just a negative number. When we replace the ammeter with a voltmeter, the circuit is no longer closed, so the current reads 0. However, the voltage is measured to be 3 volts, which comes from the two 1.5 volt batteries. The sum of the individual potential differences for a round trip around the circuit should be 0. Our graph supports this, as well does the physics principle, delta V round trip equals 0. The voltmeter doesn't affect the reading because it doesn't disrupt the flow of the current, and you can see in our graph the different values from different points. We find our R47 to be 48, our R100 to be 102, our R wire to be 0, and our R ammeter to be 0 also. For our second experiment, we set our initial conditions as a 9 volt battery, a 10 ohm light bulb and a 20 ohm light bulb, and a 200 millifarad capacitor. Our system is the circuit and our surroundings are everything else. Assumptions from before hold true. Okay, observation, the light bulb lights up and dims very quickly. This is when the capacitor is being charged, and then removing the battery powers the light bulb when the capacitor is discharged. Time for the 10 ohm, we get 6.4 seconds to charge and 8.4 seconds to discharge. The 20, we get 12.3 seconds to charge and 10.6 seconds to discharge. For the second part of this experiment, we replace the 10 or 20 ohm light bulb with a 30 ohm light bulb, but our other factors remain the same, with a 9 volt battery and a 200 millifarad capacitor, system, circuit, surroundings, everything else. Here you can see the data we collected from this experiment and the graph, which is a linear relationship. The slope of the line of best fit is 0.167842940. So when we divide -1 by that slope, we get 5.958 seconds, which is our RC experimental. Our RC model is just going to be 30 ohms times our 0.2 farads, which is 6 seconds. Our percent error will then be 0.7%. We see that there is an outlier in between 0 and 5 seconds, which could be causing the discrepancy, but the experiment is still very accurate at 99.3%. So if we had done this lab in real life and used an actual ammeter instead of an ideal simulated error ammeter, the resistance of the ammeter in the real life would not be 0. In fact, it would probably not even be negligible, so we would have had a lower measured current, but because the online simulator assumes the ammeter has a resistance of 0, we don't have that same effect. Now, if we were doing the lab in real life and used a real battery to charge the capacitor with no resistor in the circuit, the capacitor would not have charged instantly because it would need time to actually charge.